All right, now we're recording again. So at least we have that. Ugh, what a pain. Um, okay. And I don't know if there's something else going on this computer. Well, yeah, but okay. Well, we'll keep playing around with this. Okay. Now, I guess I'll also try harder to say what I'm writing as I go. Okay, so here I have written the entire process, and I'm going to write next to it the approximate operation count. So the number of floating point operations that are needed for Gauss elimination with pivoting. That is 2/3 n cubed flops or floating point operations. The pivoting is negligible if you're doing partial pivoting, so I don't even include that. The forward substitution is n squared, and then the back substitution is also n squared. So and those are negligible compared to the 2/3 n cubed. So basically 2/3 n cubed floating point operations gives you the leading order complexity of solving AX equals B. Now, but the solution that we're computing, x, is supposed to be, as we can represent it as A inverse B. So since we know that that's the solution, the important question to ask is, why not compute A inverse and then just multiply that by B? Because once you have A inverse, doing this matrix vector multiplication, A inverse times B, takes roughly 2n squared floating point operations. So it's worth asking, how expensive is it to compute A inverse? Now, way back earlier in the notes, I should mention what I'm doing right now is not explicitly in the notes. I do have stuff from chapter 1 that shows how B inverse is computed, and I will revisit that. But even then, I don't talk about it from an efficiency point of view, but I will now. So why don't we do this? So in order to compute A inverse, which I'll label as, actually I won't call it B, I'll call it C. So if I label A inverse as C, what we have to do is solve several systems of linear equations. I'm solving A Cj is equal to Ej. So Cj is the jth column of C, which is A inverse. And then Ej is a jth column of identity. And the way we get these equations is from a matrix equation. A times C is equal to identity. So I take AC equals identity. I look at this equation column by column, one column at a time, and I get that. And I have to do this for each j, 1, 2, up to n. So I'm solving n systems of equations. Each system gives me one column of the inverse. So I'm computing the inverse column by column. So I think, okay, nothing to it. Here's the cost of doing that. Well, we had to do LU decomposition with pivoting, just like if we were solving a single system. So that's 2/3 n cubed floating point operations just for that. Now we have to do solving by forward and back substitution, except we have to do it n times. So we do L Yj is equal to P Ej for each j, 1, 2, up to n. So the cost of one forward substitution is n squared, but we're doing n of them. So we have to multiply that by n. So this phase costs n cubed. So already we're wasting time. And then we have to solve the upper triangular system. It's back substitution. U Cj, so we're solving for a jth column of the inverse, is equal to yj. And we have to do that again for each j, 1, 2, up to n. So that again costs n cubed floating point operations. So the bottom line is, in order to explicitly compute A inverse, the total cost is 2/3 n cubed plus n cubed plus n cubed, so 8/3 n cubed floating point operations. So what that means is, in order to solve a system of linear equations by computing A inverse and then A inverse B explicitly, you're expending 4 times as much effort doing that than just doing Gauss elimination with pivoting and jumping to the solution directly without ever actually computing A inverse. So the moral of the story is, never, ever, 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 ever explicitly compute A inverse. Just don't do it. It's a complete waste of time. So if you have some formula that involves computing the inverse, and but typically what happens is that inverse is multiplied by a vector. So that represents, oh, you're not really computing the inverse multiplying by a vector, you're solving a system of equations with that vector as your right-hand side, and you're doing Gauss elimination pivoting, or later we'll get, actually pretty soon, actually after spring break, maybe a little bit before spring break, we'll start iterative methods. Can't wait. This is something to keep in mind, actually, on the homework, the second homework. There's at least one problem that involves computation that involves the inverse, and how do you do that intelligently? It's problem 5 on homework 2. There's 3 different matrix computations, and the key is, how do you come up with the most efficient method possible using these ingredients: Gaussian elimination, forward and back substitution, and this is the most expensive one, so you want to try to do that as little as possible. So it's not too hard to come up with an algorithm for any of those problems, but the key is, don't give me a dumb one. That's crazy slow. Okay. So any questions about computing the inverse versus doing it the faster way? Okay. All right. Now I can return to the notes. Well, I guess I should. What I just had, I should add to the notes at some point. So, still blind down there? Ashley?
Sorry, my sound keeps going in and out. But yeah, it's still blind.
Okay.
I can hear you now.
Okay, that's something. Okay. Now, yeah. Okay. Okay. I know, but shut up.
I'm just saying. Figure out, hey, we need to move it and we can't send you.
I know, but I'm proactive.
What? Are you from the coast? No reason to talk about the coast.
But you come up here? Or?
No, I'm from the coast, but I'm in Hattiesburg.
Oh, okay, all right.
People talk about Central Mississippi. I'll talk about the coast.
Okay.
It's cold with those windows out there. I can feel the breeze.
And I started to feel the breeze too, and I was like, ooh,
Did you open them?
No, I didn't. I
Oh.
closed that one. No.
We should close those.
Oh.
Hey, I'm getting cold.
Okay. I think it's up here. I feel hot. Okay. All right. Now,
Thank you.
so I mentioned early on that in numerical linear algebra, as opposed to theoretical linear algebra, determinants don't play as much of a role. However, I will briefly talk about practical computation of determinants, just because it's a natural consequence of what we have for solving systems of equations. Now, the method that is usually taught for computing determinants is a recursive one, where like you go across a row or column and you compute determinants of matrices you get by deleting a row and column. So it's done recursively, and a number of operations on the order of n factorial. But we don't need to do that. So to compute the determinant in far fewer operations than that, we can use PA equals LU in order to compute the determinant. Because we could use the very important property of determinants that the determinant of a product of matrices is a product of the determinants. So what I have here is the determinant of P times the determinant of A, which is what we want, is equal to the determinant of L times the determinant of U. Next, we can use the fact that when you have a triangular matrix, upper or lower, the determinant is just a product of all the diagonal entries. But for a unit lower triangular matrix, all the diagonal entries are 1. So the determinant of L is just 1. And then for U, we just multiply those diagonal entries together. So we have the product from I equals 1 to n of UII. So once we've gone to the trouble of carrying out Gaussian elimination, the determinant of this side is nothing to it. All right, so the determinant of A is what we're after. The last thing we need to deal with is the determinant of P. Now, so what's the determinant of P going to be? It turns out that it's an orthogonal matrix, and it's also a real matrix. So what happens in that case is the determinant is equal to plus or minus 1. Well, which is it? It turns out in this case, that's easy to tell. It's minus 1 to the S, where S is the number of row interchanges that have been performed during Gaussian elimination with pivoting. Because every time you interchange rows of a matrix, that changes the sign of determinant. So we're just looking at the number of sign changes right here. So as a result, we now have a simple formula for the determinant of A after carrying out Gaussian elimination with pivoting. So I just move this to the other side, which actually doesn't change it at all. So it's just minus 1 to the S to record the number of sign changes times the product of all the diagonal entries of U. So this formula, you're just performing order n operations, but you have to take into account you only have this information because of Gaussian elimination. So the cost really is the cost of Gaussian elimination, roughly 2/3 n cubed. But that is a whole lot better than n factorial, using the definition that's commonly taught in a class like 326. So this is the most efficient way to compute a determinant for a general square matrix. Okay. So using this formula here, once you perform all the row operations necessary to be able to use it. Okay. So questions about determinants? That's probably about all I'm going to say about determinants. rest of the semester. Okay. All right. And any luck with this board, Ashley?
It's a little bit.
Okay. As I'm about to leave it, but okay. Now, what I'm going to cover next is related to problem 3 of homework 2. Historically, students have I give this problem every time I teach this class, and people seem to find it hard. And I think in one respect it may make it a little harder than it needs to be, but I'll see what I can do to help with that without necessarily giving anything away, and see if that works this year. Okay. 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 So the theme of this section is, all right, we now know how we have an algorithm for solving AX equals B now. But here's the problem. When we solve AX equals B, using the method just described, using Gaussian elimination of pivoting and forward and back substitution, so it's going to output a solution, X. So the X is actually computed. For instance, that's maybe put out by MATLAB. And I'll call the computed solution X tilde. So I'll use this vector X to refer to the exact solution that we want and we will never be able to get. X tilde is what is actually obtained. So that is not going to satisfy our system of equations exactly. There's going to be some error involved. So there are two big questions to try to get answers to. First is, how accurate is our computed solution? Is there some way we can actually estimate the error due to, for instance, round-off error from floating point arithmetic, and so on? And second, if we can get some idea of how erroneous X tilde is, can we improve on this solution? Is there some way to perform correction to get a better solution? And fortunately, the answer is yes. So how can we go about estimating accuracy? The first thing to keep in mind is don't be fooled. There's an obvious way to try to gauge how accurate your solution is. You might think, oh, I have my X tilde. I'll go ahead and plug it in here. And we want it to satisfy it exactly, but it's going to be off. So I compute what is called the residual vector. So R is equal to B minus A X tilde. So R is our residual. Now, the thinking is this. If X tilde was the exact solution, then our residual R would be 0. We want it to be 0. We want it to be as small as possible. So you might think, oh, I go ahead and plug in my computed solution into this, get my residual, I see that the residual is small. And I think, oh, the residual is tiny, therefore my error is tiny. But that's not necessarily the case. Here's what we really want. Not the residual, we want the error in the solution, which I'll label E, and that is the exact solution minus the computed solution. That is what we really want, what we really need to be small. So the natural question to ask is, if our residual is small, is our error also small? What is the relationship between them? Is there some relationship between, like, for instance, a norm of a residual and the norm of the error that can allow us to make conclusions about whether a small residual actually implies a small error? Okay. So here's how we can get that relationship. It actually comes from the definition of the residual. Okay, so what I can do is I can take my error that I want, E, and I'm going to go ahead and multiply it by A. Now, error is defined as the exact solution, X, minus my computed solution, X tilde. Now distribute, so that's A exact X minus A computed X. Now, since this is the exact solution, A times X is equal to B minus AX tilde, but that is my residual. So if I summarize this, A times the error equals the residual. So we do have a simple relationship between the error and the residual, but now we want to, from that, figure out what is the relationship between the size of the error and the size of a residual. So now I'll rearrange this by moving A to the other side. So it's A inverse times R. So in fact, if we compute a residual, we could multiply it by A inverse and get E. Or we could, well, we would not do that exactly. We could solve a system involving R as the right-hand side and E is our unknown. And we actually will do that in a little bit. But right now we're just focusing on the analysis. So I'll go ahead and take the norm of both sides. So the norm of E is less than or equal to the norm of A inverse times the norm of R. And then what I'll do is, I'm going to multiply and divide by the norm of B. Now, this B up top, I can replace with AX. But norm of AX is less than or equal to the norm of A times the norm of X. So I can split this up into two norms. Okay. And then I can take this X, I'll divide by that. So now I have a relative error. Norm of B over norm of X, so a relative error in my computed solution is less than or equal to norm of A times the norm of A inverse times the relative residual, the norm of relative residual, because I'm scaling it by the norm of B. So I've relative error over here, relative residual over here. Look at the amplification factor, norm of A times norm of A inverse. We've seen that before. What do we call that? What? Yes, that is a condition number. So now we have a problem, because what it says is we go ahead and compute our solution x tilde, that's contaminated by round-off error, and then we find that even though the residual is small, the norm of our residual could be amplified by the condition number and giving us the norm of the relative error. So what that means is if A is ill-conditioned, we could have a nice tiny residual and a nice large error. So small residual does not necessarily mean that the error is small. Okay. But at least now we have a way of estimating what that error is, because we solved a system AX equals B approximately to get our computed solution. Now we can solve this system with our residual as a right-hand side to get an error estimate. So that is our ticket. So this relationship right here lets us do two things. Answer both those questions, really. It lets us estimate the error, because we go ahead and solve that system, because the residual R is something we can compute. And the second thing is it lets us improve our computed solution. And that leads to a process called iterative, actually it has many names. Iterative improvement, also known as iterative refinement, also known as residual correction, and probably many other things I'm not thinking of right now. Okay. So for now we'll call it iterative refinement, and I'll give the algorithm for that. Okay. All right, so iterative refinement. First I'll give the main idea behind it, and then I'll give a full algorithm. Main idea is if I take the definition of error, so that would be exact solution minus computed solution. Well, I just rearrange it. So my exact solution is my computed solution plus the error. But the error satisfies this equation. So the idea is this. We compute the residual R, which is B minus AX tilde. Then what we do is estimate the error by solving AE is equal to R. And then we update our computed solution by just adding on this error using this relationship. What we get is not the exact solution, it's an updated computed solution that should be more accurate than before. And then the key part of this, we repeat this process. So we will keep computing residual, keep updating the solution until there's nothing more to be gained by it. And at some point, we won't gain anything more because every part of this process is still contaminated by round-off error. So we can only gain so much. And I'll talk about how much we can gain in just a little bit. Okay, so so now I'll write down the full algorithm, and this is something that you will use in some form in homework 2, problem 3. Okay. So first, what you do is choose some level of accuracy that you're aiming for. So an error tolerance, so I'll just call it TOL, tolerance. Next, I'm going to set my computed solution initially to be the 0 vector, and I'll set my residual initially to be my right-hand side, B, which makes sense because what is the residual? B minus AX. Well, if X is 0, then I'm just going to get B. So this computed solution and this residual are consistent with one another. And now I'll start a loop that keeps updating this solution and residual. So inside this loop, I'm going to do my error estimation. So I'm going to solve a system, AEK is equal to RK. So residual goes to the right-hand side, and we solve the system using the same old method, Gaussian elimination, forward and back substitution, and we get our error estimate. Now, since it's our error estimate, we want this error to be small. So we'll go ahead and check, is it small? So if the norm, and we can use any norm, but we'll go ahead and use the infinity norm here. So if the norm of the error is small enough to our satisfaction, then we'll stop. We'll go ahead and quit this loop immediately. Or in MATLAB, you use a break statement. Okay, otherwise, we'll update everything. So our new solution, x tilde, and I'm label these as iteratively, so x tilde k plus 1 is equal to our previous computed solution xk, and we'll just add on the error. Okay. So it's this update right here. And then our new residual. Now, we know what the formula for residual is. It's B minus A times computed solution. So you might think, oh, that's what I'll do here. But I'm not. And I'll explain why shortly. So our new residual is equal to our old residual minus A times our error. So that is mathematically equivalent to what we think of as residual, B minus AXK plus 1. So I'll make a note of that here. Okay, and that's the end of our algorithm. So, so at this point, we have a new solution, a new residual, and then we'll repeat this process to get a new error estimate, check if it's small enough, keep updating solutions. We'll just keep doing this until we're finished. Okay. Now,
When you're done.
yes?
How do you know when you're finished?
Right here. If your error becomes small enough, that's when you quit. So yeah, this is our this if statement is our convergence test right here.
Okay.
Because what's going to happen is at some point, well, one or two things are going to happen. Either this will get small enough, or well, actually, what you'll find is your solution will just stop changing because E will be so small.
Okay.
Yeah. Now, so there's two things I want to explain about this algorithm. Okay, first this. How come this formula is better to use than this one, which is just the definition of a residual? The thing to keep in mind is both formulas involve a subtraction. So we have to check, are we recording cancellation error by either of these subtractions? Well, since it's a process that keeps reducing the error, keeps making it smaller and smaller, driving it to 0, this vector, ek, is going to 0, therefore aek is going to 0, and rk, the residual, that is also going to 0. So both these vectors are getting smaller and smaller. And the difference between them, our new residual, should also be getting smaller and smaller. So we're subtracting something that's supposed to be small and getting something else that's supposed to be smaller. So this is actually safe as far as catastrophic cancellation is concerned. What about this one? Is that safe from a cancellation point of view? Keep in mind that the difference between them is supposed to go to 0.
Well, probably no, because that's long enough. That's great.
I set myself up for that one, didn't I?
Yes.
Okay, but give me a better answer.
No, because P can be large.
Yeah, the point is, neither one of these is going to be 0. So, yeah, they may not necessarily be particularly large, but so this is a more insidious form of catastrophic cancellation where these could be whatever size they want. The point is they're not going to 0. And the difference between them is going to 0. So it's actually the opposite of what happened in that case I told you about with in the Iraq War, where you're subtracting numbers that were getting larger and larger, and the difference between them was a consistent level of smallness, but it was always relatively small. It was getting relatively smaller compared to the numbers you're subtracting. This is the opposite. These are staying a relatively constant size, but the difference between them is getting smaller and smaller. So the point is, catastrophic cancellation happens when the difference is small relative to the size of what you're subtracting. And however that disparity comes about doesn't matter. The point is it's a bad thing. So because this difference is getting smaller and smaller, and neither one of these is going to 0, this is a bad approach to computing a residual. This is much safer. Okay. Okay. Now, so that's one thing I want to point out. The second thing I want to point out, and this is particularly important for the related homework problem, is in this key step here, where we're estimating the error, we're solving a system of equations involving the residual. So our error estimate is an approximation to the true A inverse times our residual. And I say approximately equal to because, of course, this computation is going to be erroneous. There's going to be some round-off error involved. However, if you can also think of this as being equal to, like exactly equal to the true inverse of a matrix A tilde that is near A. So in other words, this is the approximate solution of our true problem of computing this. But it's also the exact solution of a nearby problem. So I say, and what I'm saying here is that A tilde is an approximation of A. So this part right here is something you need to keep in mind for problem 3 of homework 2. That you can view this error estimation step from this perspective. And this is why I spent a little time earlier in the semester covering backward error analysis, because backward error analysis, you're assuming that your erroneous solution is actually the exact solution of a nearby problem. So that perspective will be helpful, because what you're going to do in this problem is you're going to make minor modifications to this iterative refinement algorithm to solve that problem. And because what happens every year is students all rack their brains or bang their heads against a wall trying to figure out how to use iterative refinement for a problem at hand, and it just goes badly. So I'm trying to save you guys some strife here, and we'll see how that goes when you get around to that. Okay. But at this point, I've done what I can, I think. Okay. Now, so the last things I want to point out about this iterative refinement algorithm is, does this really work? Because it seems kind of strange that when you're solving AX equals B using Gaussian elimination and forward-back substitution, you're using whatever arithmetic is available to you. You're performing the correct algorithm, and you just have round-off error, and you get a solution out that's going to be erroneous. Why should this, which does more of the same erroneous floating point arithmetic, why should that help at all? Does it help? How much does it help? Okay, so fortunately, I can say a little something about that. Okay, so what can be said about this? The effectiveness of iterative refinement. Okay. Well, for one thing, it is absolutely essential, in order for this to do any good, that all of the residuals are computed very accurately. In fact, if it is possible on the computer you're using to have some sort of higher precision, then you want to use that extended precision, if available, to compute the residuals. So if you're using a higher precision for residuals than everything else you're computing. For example, say if you're programming in C or C++, you have a float type that's 4-byte storage, that's single precision. And then you have your double, that's 8 bytes, it's double precision. So you could be, for instance, performing the bulk of your computations in single precision, except for the residual, b minus a x tilde, you do just that computation in double precision. And the idea is you want an answer that's as accurate as possible, at least in single precision. And some architectures have some sort of extended precision that goes beyond double. So use whatever precision your computer has. Okay, so what we can conclude, or what can be proven, is if the condition number of your matrix A times your unit round off is less than or equal to 1. So A is allowed to be ill-conditioned to some extent, but not ridiculously so. So that, for instance, because our unit round off for double precision is like on the order of 10 to the minus 16. So you can have a matrix that's kind of bad, like 10 to the 12th condition number, and this will still be satisfied. So if it's not outrageously ill-conditioned, and the residuals are computed in extended precision, so at least extended relative to what you have. So let's see, it'll also work, for instance, if we're dealing with single precision here, and you're using double precision. So in other words, just a higher level of precision. Then what happens is your computed solution converges to a solution with all digits correct in that lesser precision. So for example, if you're doing everything in double precision, but you compute RK using some extended precision, then iterative refinement will give you a solution that, as from a double precision point of view, actually is exact. All of those digits are correct. So can't really ask for anything more than that. So under these hypotheses, yes, this really does work. You can get, in some form, to the limits of your floating point system, really get the exact x. Once you compute it, and the thing is, iterative refinement is pretty cost efficient because you're solving systems repeatedly using the same matrix A, so you only have to do Gaussian elimination with pivoting once. And then everything that actually happens during that iterative refinement loop involves just forward and back substitution using different right-hand sides, your residuals. And then matrix vector multiplication to compute the new residuals. So each iteration of iterative refinement takes order n squared floating point operations. So you're just generally doing a few of those iterations. So the overhead of iterative refinement compared to what you already did for Gaussian elimination with pivoting is negligible. Okay. So any questions about iterative refinement? All right, so I only have 3 minutes left. So actually, this is a natural stopping point. So so next week I will get into special systems of equations like symmetric positive definite banded systems. And if we have time before spring break, I will start iterative methods, and we'll do a whole bunch of that after spring break. Okay. Any last questions? Okay. And don't wait too long before starting homework 2. Some of those problems are actually not bad, but some of them are. But actually, yeah, everything, I've covered almost everything needed for homework 2. The only thing is, on Monday I'll cover symmetric positive definite matrices, which is relevant for problem 1 of that assignment, and then you'll be able to do everything. Okay. Yeah.
We talked about number 3.
Yeah.
Form of A minus capital. So capital
Okay, there's a lot of noise in this room. Can you repeat that?
yeah. So on top of number 3,
Yeah.
it says suppose that the form of A minus B is small.
Yeah.
So would this be the A tilde that we've been talking about?
Yes.
Yes.
Yeah. So for those of you who heard that, this problem just became a lot easier.
Sorry.
Honestly, considering how much trouble this problem has caused over the years, that's quite all right.
Huh? What?
Real sequence.
I guess so. I don't pay attention.
Oh well. Well, also, well, yeah. Even though I won't talk about problem one and related material until Monday, well, you would definitely know how to do about problem one because you know so much about symmetric positive definite matrices.
Dr. Lamb,
Yes.
I'm gonna. Okay.
Okay, go ahead.